how do we search in a B tree? Okay, so we're going to talk about B tree search. Okay, and let's talk about it here as it is X comma K, where we are going to be doing tree search on node X and key K. When we call it the first time, when we want to do the search in the full tree, we really call B tree search on t.root, so the root of the tree, and the key K that we are interested in. Okay, so how would search function work in the case of B trees? Well, it's very simple. The first thing is that we start with the node X. So this is node X, and this node, it will have its own keys, K2 all the way to whatever here. Okay, so now the first thing we need to check, is K one of these keys? Okay, so if K is one of these keys, then we just said, okay, it's key 2, return, and we are done. We just return that the node X and key 2 are what you are looking for. But if it's not there, and we'll keep looking for K, and then we say, okay, if K is not one of the keys in this node, let's find which child it would be in, because remember that there is an important property about the keys in the node as well as the keys in the children, that they have to be in non-decreasing order. So imagine that K is larger than K2 but smaller than K3. Then K should be in the subtree that is rooted at this pointer between K2 and K3 here, okay, which is x.c3. Okay, so this will be x.c3. So we come to this node here and ask, is the key in this one? If the key is in this one, then we return, we say, okay, x.c3 is the node you are looking for, otherwise repeat, and then we go to the next node, and we look, is the key there? If it's yes, then return, otherwise find which other node it is in of the children. So we keep just basically traversing like this. Now, one important thing I want to say is the following. As I said, these nodes and this tree structure is not in the main memory. So when I look for the key in the first node, in the root, if I don't find it, I have to do the operation of disk read, for example, x.c3. What this means is that now I have to go fetch that node that is pointed to by x.c3 from the disk. Okay? And if this node here, the same thing, I need to do disk read on this one, and I have to do disk read as well on this one, and so on. So what I'm saying is, when we call this operation on the root of the tree, okay, so the root of the tree is in the main memory. We look at the keys in that node. If the key we are looking for is there, we are done. We say it is in the root and it is the 7th key. If it's not, we need to start traversing a path from that root to the leaves. Okay, the key will be somewhere there in that path. If it is in the tree, it will be somewhere there. So when we fetch the first child to look for that, we have to be doing disk read. And if I need to fetch a child of the child, I have to do disk read, and so on. Okay, so it's almost like binary search. The only two differences are, the first one is that the decision is not binary at every node. We don't say, if the key you're looking for is smaller than the key of the node, go left, otherwise go right. No, we can have more than left and right. We can have 17 children, and we need to check which of the 17 children we need to go to. This is the first difference. The second difference is that when you want to go to the next child, the next child node is not in the main memory. You have to do disk read. Okay, so we actually put that disk read in the pseudocode, because when we are doing the analysis of the running time, we want actually to look at how many times we are doing disk read operations. Okay, so it's as simple as that. So if I want to write the pseudocode for B tree search, from node X and key K, I can start by initializing I. This is what is this? This is the index. I'm gonna now scan the keys of node X in search for K. Okay, so I will say now, while I is smaller than or equal to x dot n. So I'm going to scan all the x dot n keys of node x, and k is greater than x dot. So I will go from left to right, from the first key to the second to the third, and so on. As long as the key I'm looking for is larger, keep just going to the next key there. We just keep advancing that index, okay? Once we are done, how do we get done here? Either I has exceeded x dot n, so we did not find it, or the key is there, or we have hit that x dot ki that is smaller than or equal to k, okay? Or larger than or equal to k. So now we say that if I is smaller than or equal to x dot n, and k x dot key I here, okay, so the ki is the key dot I, we can now return that we found the key in node x, and it is ki I there, okay? So this if statement here, we are saying, yes, we found the key, and it is the key k, and it is ki, the key ki in node x. If it's not, and if x is a leaf, okay, if x is a leaf, then we have hit a leaf, we could not find ki, or k, sorry, then we basically return nil, okay? We could not find it. Else for this if here, okay, else, what do we do? Now, we did not find, we get to this else, it means that we did not find the key, but it's somewhere here. We are now going to be looking for x dot ci, for example. So now we need to look in that child here. So the first thing we need to do is disk read x dot ci, and now we can apply the same function recursively on this new node instead of x. So now we can do return b3 search on x dot ci with the same key k. This is really how we do the search. Again, if you look at this, there is nothing harder or more involved than doing search on a binary search tree. Unlike binary search tree, the decision is not, just do we go left or right? It's which of the n keys or which of the n children we go to, and this is what this function is saying. And again, the other difference is this issue of disk read here, that we have, once we need to access a child, we have to fetch it from the disk. Now, what about the running time of this function here? If we look at the running time of this function, really the problem is the disk read here. And these disk read operations, we know that this case here, in the worst case, this is going to be done on the order of log to the base t of n, okay? Because we have already reasoned on the height of the tree, and this operation, in the worst case, is we are going to go from the root to a leaf, okay? Because if the key might be in a leaf, or the key is not in the tree, but we had to traverse all the way to a leaf to know that. In this case, the running time, or the number of times we have to do disk read is on the order of log n to the base t, okay? Now, this is the number of reads, but for every time we read a node, we have to do CPU time, right? We have to do time on whatever we loaded into the main memory. So all this work, above this, before this command, is done in the main memory. So we know that this is one operation. This one here is on the order of t, okay? So this is O of t. Why is it on the order of t? Because remember that the number of keys in the node is somewhere between t minus 1 and 2t minus 1, which is O of t. These operations here, each one of them, in this case, is O of 1 here, right? So the if statement, the return, and checking if a node is a leaf, and so on, these are O of 1. So what do we get here is that for every time we get to this line here, every time we get to this line, we have already done O of t work. Now we get to this line in the worst case, O of log n to the base t. Therefore, the total amount of time here, the total amount of CPU time is O of t times log n to the base t. Okay, so this is the total amount of CPU time. Okay, and again, while I'm writing the log to the base t, just to emphasize that t plays a role here in this running time, please keep in mind that log n to the base 2 and to the base 5 and to the base 15, they are asymptotically all equivalent. Okay, so asymptotically the t is not going to make a difference whether it's 2 or 15, it's the same thing, but in practice it will play a big role here, because in practical applications or implementations of B-tree, it is common for t to be on the order of thousands. Okay, t could be 1,000 or 10,000 and so on. So log to the base 2 and log to the base 10,000 in practice will be very different. Asymptotically, again, they are, one is order of the other. Okay, so this is how we would do the search. Again, it's on the order of, it's an order of log n times t, and the number of disk reads, which is again a costly operation here, is O of log t of log n to the base t.